Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles with an internal lunge between them at this point. Let's define this point as point N. So actually the two circles touch each other at point N. Point N is the point of contact between those two circles, and AC equals to 9 units and dB equals to 4 units, and the small circle has 3 lunge points, or has 3 tangents. This is the first tangent to the small circle. This is the second tangent to the circle, and this is the third tangent to the small circle. Okay. We also know that this angle is a right angle, and also this is a right angle. It equals to 90 degrees, and actually this angle also must be equal to 90 degrees, because of the rule that the sum of the angles in the upper side of a straight line equals to 180 degrees. So if this is a right angle, then this angle must complete the sum to 180 degrees, so it must be a right angle also. And for the same reason, this is also a right angle. So first of all, we will define the center of the small circle as point Q. Again, point Q is defined as the center of the small circle, okay. This is point Q, that is the center of the small circle, and we will define point P as the center of the big circle, So this will be point P, the center of the big circle. Okay, so I'll write it down that point P is defined as the center of the big circle. So I'll read again the things that I want. Point Q is the center of the small circle, and point P is the center of the big circle. Okay, and we will also define the radius of the small circle as small r. Small r is the radius of the small circle, and capital R will be defined as the radius of the big circle. Okay? So small r is the radius of the small circle, and capital R is the radius of the big circle. Okay? In the next step, we will draw three radiuses of the small circle that starts from the center of the circle and touches the circle at the launch points between the circle and its tangents. Okay, so the first radius of the small circle will start from the center of the circle, that is to say from point Q, and the radius will end at the launch point between its tangent and itself. So let's define the launch point between this tangent and the circle as point S. Okay, so actually, again, the radius of the small circle starts from the center of the circle, that is point Q, and ends at point S, that is the launch point between the tangent to the circle. And we will also draw the second radius of the circle that starts from the launch point, from the center of the circle, and ends at the launch point between the circle and this tangent. Let's define the launch point between the tangent and the circle as point Z. So QZ is the radius of the small circle. It starts from the center of the circle and ends at the launch point. Then we will draw the second radius of the small circle that starts from the center of the circle and ends at this point, that is the launch point between the tangent and the circle. Let's define the launch point between the tangent and the circle. This point is point M. Again, point M is the launch point between the circle and this tangent. Okay, so we draw 3 radiuses of the small circle that touch the launch points of this circle, the launch points between the circle and its tangent. This is the first launch point between the circle and its tangent, point S. Point Z is the second launch point between the circle and this tangent, and point M is the third launch point between the circle and this tangent. Okay, and in the next step I will present you a rule. Rule number 1. Rule number 1 states that the tangent to the circle is perpendicular to the radius drawn to the launch point. So I'll read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius drawn to the launch points. So, according to rule number 1, whenever you draw a radius that is drawn to the launch point, like in this example, then the tangent will be perpendicular to that radius. Okay? Again, according to rule number 1, the tangent to the circle is perpendicular to the radius drawn to the launch point. So actually, this radius is drawn to the launch point between the circle and its tangent. Therefore, according to rule number 1, the tangent is perpendicular to that radius, that is to say, this is a right angle. Okay? And the same rule is also in this radius. This radius is drawn to the launch point, that is point Z. Actually, it touches the launch point. It touches point Z, that is the launch point. Therefore, the tangent is perpendicular to that radius. That is to say, this is a right angle. It equals to 90 degrees. Again, whenever you draw a radius that is drawn to the launch point, or it touches the launch point, then that radius will be perpendicular to its tangent, or the tangent will be perpendicular to that radius. It is the same thing to say that the radius is perpendicular to the tangent, or the tangent is perpendicular to the radius. So whenever you draw a radius that is drawn to the launch point between the circle and the tangent, then that radius will be perpendicular to the tangent. And also here we have a radius that is drawn to the launch point. Actually, it touches the launch point, that is point M. Therefore, that radius is perpendicular to this tangent, that is to say, this is a right angle, it equals to 90 degrees, and also this angle is a right angle because of the fact that the radius is drawn to the launch point and it touches the launch point. Therefore, the radius will be perpendicular to this tangent. Okay? Again, rule number 1 states that the tangent to the circle is perpendicular to the radius drawn to the launch point. And here we have 3 radiuses that all of them are drawn to the launch points between the circle and its tangent. Therefore, according to rule number 1, the tangent is perpendicular to the radiuses. The tangents are perpendicular to those radiuses, so you can also say that those radiuses are perpendicular to their tangents. Okay? This radius is drawn to the launch point, therefore this is a right angle because that radius will be perpendicular to this tangent, and also this radius is drawn to the launch point, that is point M. Therefore, the tangent is perpendicular to that radius. Therefore, this is a right angle, and also this angle is a right angle, and also this radius is drawn to the launch point, that is point Z. Actually, it touches the launch point. Therefore, the radius is perpendicular to this tangent, or the tangent is perpendicular to that radius, that is to say, this is a right angle. Okay? So, actually, we have here quadrilateral QZMD. Okay, on quadrilateral QZMD has three right angles. This is the first one, this is the second one, and this is the third one. Okay? Quadrilateral QZMD is three right angles. 1, 2, 3. And the sum of those three right angles equals to 270 degrees. The sum of those angles is equal to 90 degrees times 3 is 270 degrees. Okay? Quadrilateral QZMD has three right angles, that the sum of those three right angles equals to 270 degrees. This quadrilateral has three angles, that the sum of them is 270 degrees. Okay? And we have a rule number 2. Rule number 2 states that the sum of the angles inside the quadrilateral equals to 360 degrees. I will write it down. According to rule number 2, the sum of the angles inside a quadrilateral equals to 360 degrees. So I will read rule number 2 again. According to rule number 2, the sum of the angles inside the quadrilateral equals to 360 degrees. So actually on quadrilateral QZMD we have three angles that equals to 270 degrees. Okay, on quadrilateral QZMD or quadrilateral QZMD as three angles that the sum of them is 270 degrees. Okay, quadrilateral QZMD has three angles that the sum of them is 270 degrees. And according to rule number 2, the sum of the four angles inside the quadrilateral equals to 360 degrees. So if we define the size of the fourth angle as y is the size of the fourth angle on quadrilateral QZMD So actually, according to y is the size is defined as the size of the fourth angle on quadrilateral QZMD. Therefore, according to rule number 2, that states that the sum of the angles inside the quadrilateral equals to 360 degrees, 270 degrees, that is the sum of the three angles, plus the size of the fourth angle, must be equal to 360 degrees. Again, it is according to rule number 2. Again, according to rule number 2, 270 degrees, that is the sum of the three angles of quadrilateral QZMD plus the size of the fourth angle, that is y, must be equal to 360 degrees. Okay, so here we will subtract 270 degrees from this equality, and we will get that y equals to 360 degrees minus 270 degrees is 90 degrees. So actually the fourth angle of quadrilateral QZMD is also a right angle. Okay, so actually this angle is a right angle. So actually quadrilateral QZMD as 4 right angles. Okay. Quadrilateral QZMD as 4 right angles. Okay, quadrilateral QZMD, this quadrilateral has 4 right angles. Okay, and we have rule number 3. Rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. Okay, and we do rule number 3 again. According to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. So actually quadrilateral QZMD has 4 right angles, and therefore it is a rectangle. And therefore it is a rectangle. Okay, quadrilateral QZMD has 4 right angles, and therefore it is a rectangle. This is according to rule number 3. Okay, So we have also rule number 4 that states that according to rule number 4, the opposite sides of a rectangle are equal to each other. So I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. So actually we know that quadrilateral QZMD is a rectangle according to rule number 3 because it has 3 right angles, and therefore according to rule number 4 the opposite sides of this rectangle are equal to each other, that is to say QZ equals to MD. Okay, so according to rule number 4, QZ equals to MD. Okay, QZ is opposite to MD. Therefore, according to rule number 4 that states that the opposite sides of a rectangle are equal to each other, QZ equals to MD. QZ equals to MD. But we know that QZ is the radius of the small circle. Okay? QZ equals to small r, it is the radius of the small circle. Okay? QZ equals to small r. Okay? So from this equality we can derive that r equals to MD. Okay, r equals to MD. Okay, r equals to MD. So we can write here that MD is equals to the radius of the small circle, and actually we have quadrilateral SQCM that also has 3 right angles. Therefore, according to rule number 2 that states that the sum of the angles of a quadrilateral is equal to 360 degrees, this angle also must be equal to 90 degrees. So quadrilateral CM has 4 right angles, therefore according to rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. Quadrilateral SQCM is a rectangle, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. Therefore, SQ equals to CM according to rule number 4. But we know that SQ equals to small r and CM equals to SQ, so CM also must be equal to small r. So I write here that CM equals to the radius of the small circle. Okay. So CM and MP equal to R. In the next step, we will define PM as X. That is to say, PM equals to X according to our definition. Okay, PM equals to X. But what is the size of line segment CP? CP equals to CM minus PM. Again, CP equals to CM minus PM. And CM actually is the radius of the small circle, is small r, and PM is X. So CP equals to CM minus PM, that is to say CP equals to small r minus X. Okay, CP, line segment CP equals to small r minus X. Okay, so in the next step we will we'll calculate the radius of the big circle in 2 different ways. We know that AB is the diameter of the big circle. That is to say, AB equals to 2R to 2 times capital R. That is actually, it is R plus R. Yes, 2R is R plus R, capital R plus capital R. And the center of the big circle is at point P, so capital R plus capital R is actually AP plus BP, because AP equals to capital R and PB is also the radius of the big circle. Okay, we have this equality that states that AB, that is the diameter of the circle, equals to 2 times the radius of the big circle. That is to say, it is capital R plus capital R, and AP equals to capital R, and PB also equals to capital R. So we create two expressions for the radius of the big circle. The first one is AP equals to capital R. P is the center of the circle, so AP equals to the radius of the big circle, and PB is also the radius of the big circle. So the second equation will be also PB is also equals to the radius of the big circle. Okay, so we have here two equations for the radius of the big circle. AP equals to capital R and PB also equals to capital R, because P is the center of the big circle. So actually in the next step we will calculate the value of AP. AP equals to capital R, but what is the value of AP? AP equals to AC plus CP. Again, AP equals to AC plus CP. Okay, AP equals to AC plus CP. Again, AP equals to AC plus CP. But what is the value of AC? AC equals to 9 units according to what is given us in the question. So AC equals to 9 units. And we have already found out that CP equals to small r minus x. Okay? So in total we got that AP that equals to R equals to 9 plus R minus X. Okay, so we can write down that capital R, that is the radius of the big circle, equals to 9 plus small r minus x. So we have the first equation for the radius of the big circle, but we also know that the radius of the big circle, or PB, also equals to the radius of the big circle. Okay, PB equals to the radius of the big circle. But what is the value of PB? PB equals to PM plus MP plus DB. Okay, so from the drawing we can see that PB, that equals to the radius of the big circle, equals to PM plus MP plus BD. Again, PB equals to PM plus MP plus BD, or DB. But what is the value of PM? PM equals to X according to our definition, and MP is the radius of the small circle, small r, and DB equals to 4 units according to what is given us in the question. So we got that p bit is equals to capital R equals to x plus small r plus 4. So I'll write again equation number 2. According to equation number 2, capital R equals to x plus small r plus 4. So we have the first equation for the radius of the big circle. According to equation number 2, capital R equals to x plus small r plus 4. So we actually have two equations for the same radius, the radius of the big circle. So we will create equation number 3 that states that the radius of the big circle according to equation number 1 equals to the radius of the big circle according to equation number 2, because we are talking of the same radius. Okay, so actually equation number 3 states that capital R equals to capital R, and capital R according to equation number 1, that is 9 plus small r minus x, equals to capital R according to equation number 2, that is x plus small r plus 4. Okay, again, equation number 3 states that the radius of the big circle according to equation number 1 equals to the radius of the big circle according to equation number 2. So here we have r in this side of the equation and small r in this side of the equation, and we have small r on the other side of the equation, so we can cancel r. And what is left after we cancel r from equation number 3 is nine minus x equals to x plus 4. Okay, so that is what is left after we cancelled r. 9 minus x equals to x plus 4. Here we will subtract 4 from this equality, and we will get that nine minus 4 is 5, minus x equals to x. Okay, we got that 5 minus x equals to x. Here we will add x to this equality, and we will get that five equals to 2x. Okay, we got that 5 equals to 2x. Here we will divide this equality by 2 in order to get the value of x. So x will be equal to 5 over 2, that is 2.5 units. So x equals to 2.5 units. Okay, we found out that x equals to 2.5 units. Now we can return to equation number 1. Equation number 1 states that the radius of the big circle equals to 9 plus r minus x. Okay, that is equation number 1. We can substitute x by 2.5 units in equation number 1. Okay. And we will get that the radius of the big circle equals to 9 plus small r. So we substitute x by 2.5 units minus 2.5. So we got that capital R equals to 9 plus R minus 2.5. 9 minus 2.5 is 6.5. So we got that the radius of the big circle equals to 6.5 plus R. Okay, the radius of the big circle equals to 6.5 plus R, and we have already found out that x equals to 2.5 units. So in the next step I will present you a new rule, rule number 5, and we will implement rule number 5 in our two circles. Okay. So actually rule number 5 states that if two circles have an internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. Rule number 5 states that if two circles have an internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So according to rule number 5, if two circles touch each other internally at a certain point, then the distance between their centers will be equal to the difference between the big radius to the small radius. Okay, so we can implement rule number 5 in our circles, because actually we have here two circles that have internal length between them at point N, that touch each other at point N internally. Therefore, according to rule number 5, the distance between their centers, the center of the small circle is at point Q, and the center of the big circle is at point P. Therefore, the distance between their centers is QP. So, according to rule number 5, QP, that is the distance between their centers, will be equal to the difference between the radiuses. The difference between the radiuses is capital R minus small r. Okay, so according to rule number 5, QP equals to capital R minus small r. Okay, so here we can add small r to this equality, and we will get that QP or R, capital R, equals to QP plus small r. Okay, we got that capital R, the radius of the big circle, equals to PQ plus small r. And we have already found out in equation number 1 that capital R equals to 6.5 plus small r. Okay, we have already found out that capital R equals to 6.5 plus small r. We have two equations for the same radius. So, of course, they are equal to each other because we are talking on the same radius. So we can create equation number 5 that states that the radius of the big circle, according to equation number 1, equals to the radius of the big circle according to equation number 4. Okay, so again, equation number 5 states that the radius of the big circle according to equation number 1, that is 6.5 plus small r, equals to the radius of the big circle according to equation number 4, that is actually QP plus small r. Okay, that is equation number 5 that states that capital R equals to capital R. Here we have small r in this side of the equation, and we have small r on the other side of the equation, so we can cancel r. And after we cancel r, we will get that PQ equals to 6.5 units. Okay, we got that PQ equals to 6.5 units. Okay, PQ actually, that is the distance between the centers of those two circles, equals to 6.5 units, and we have already found out that x equals to 2.5 units. Okay, so We have the values of P, Q, and X. In the next step, we will connect together by a straight line points P and Q. We connected together by a straight line points P and Q. And actually we created here a triangle QPM. Triangle QPM is a right triangle because angle QMP is a right angle. Okay, so in triangle QMP, it is a right triangle okay. The green triangle QMP is a right triangle, so actually we can implement the Pythagorean theorem in the right triangle QMP. Okay. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. And in right triangle QMP, the square of the hypotenuse is PQ square. PQ square equals to the sum of the squares of the perpendiculars equals to PM square plus QM square. Okay, so the implementation of the Pythagorean theorem in triangle QMP is that PQ square, the square of the hypotenuse, equals to the sum of the squares of the perpendiculars equals to PM square plus QM square. But we have already found out that PQ equals to 6.5 units, so PQ square is 6.5 square equals to PM square. PM equals to X, and we have already found out that X equals to 2.5, so PM square is 2.5 square, and QM is the radius of the small circle, so QM square is R square. So we got that 6.5 square equals to 2.5 square plus small r square. 6.5 square is 42.25 and 2.5 square is 6.25, so I write it down. So we got that 42.25 equals to 6.25 plus r square. Here we'll subtract 6.25 from this equality and we will get that 42.25 minus 6.25 is 36. 36 equals to r square. So we got that 36 equals to r squared. Here we will take a root out of this equality and we will get the value of r, that is the radius of the small circle, equals to the root of 36. The root of 36 is 6, so the radius of the small circle equals to 6 units. Okay, so I found out that the radius of the small circle equals to 6 units, so the radius of this small circle, that is to say small r, equals to 6 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the radius of the small circle. We have here two circles that have internal length between them at point N. They touch each other at point N. And we also know that AC equals to 9 units, BD equals to 4 units, and this angle is right angle, and also this angle is right angle, and the small circle have 3 tangents. This is the first tangent, this is the second tangent, and this is the third tangent. Okay, and we want to find out the radius of this small circle. Okay, first of all, we define the center of the small circle as point Q, and we also define the center of the big circle as point S, as point P, and we define the radius of the small circle as small r, and the radius of the big circle as capital R. Then we draw 3 radiuses that starts of the small circle. We draw 3 radiuses of the small circle that starts from the center of the circle and ends at the launch points between the tangents to the circle itself. So here point Z is the launch point between the circle and this tangent. Point S is the launch point between the circle and this tangent, and point M is the launch point between the circle and this tangent. Okay, so we have a rule, that is rule number 1. According to rule number 1, the tangent to the circle is perpendicular to the radius drawn to the launch point. Okay, so according to rule number 1, this tangent is perpendicular to this radius, because this radius is drawn to the launch point, that is point Z. Therefore, this tangent is perpendicular to this radius. That is to say, this is a right angle, it equals to 90 degrees. And also we have the second radius that is drawn to the launch point. Therefore, according to rule number 1, this radius is perpendicular to its tangent. That is to say, this is a right angle, and also the third radius that is drawn to the launch point is perpendicular to this tangent. Okay, So this is a right angle, and this is a right angle according to rule number 1. And actually, this quadrilateral QZMD has 3 right angles, and the sum of those 3 right angles equals to 90 degrees times 3 is 270 degrees. And we have a rule number 2, that states that the sum of the angles inside the quadrilateral equals to 360 degrees. Okay, so actually, and especially in this quadrilateral QZMD, the sum of its 4 angles must be equal to 360 degrees. So if we define the size of the fourth angle as y, then according to rule number 2, the sum of the angles inside quadrilateral QZMD must be equal to 360 degrees. That is to say, the sum of the 3 angles, that is 270 degrees, plus the size of the fourth angle, must be equal to 360 degrees. Okay, we subtracted 270 degrees from this equality, and we found that y, that is the size of the fourth angle, equals to 90 degrees. So actually this angle equals to 90 degrees. This is a right angle. So actually quadrilateral QZMD has 4 right angles. And we have rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. So according to rule number 3, quadrilateral QZMD is a rectangle, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. So the opposite sides of the rectangle QZMD are equal to each other. That is to say, QZ equals to MD. According to rule number 4, QZ equals to MD, but QZ is the radius of the small circle, so QZ equals to R. So from this equality, MD equals to QZ equals to small r, we can derive the equality that R equals to MD. Okay, so this line segment MD equals to small r. And we repeated on the same process on quadrilateral QSMC. This quadrilateral has 3 right angles, so the fourth angle must be equal to 90 degrees according to rule number 2. And this quadrilateral that has 4 right angles, it is a rectangle according to rule number 3, and according to rule number 4, the opposite sides of any rectangle, and especially rectangle QSMC, are equal to each other. That is to say, QS equals to CM. Okay, QS equals to CM, but we know that QS equals to small r. Therefore, CM that equals to QS must be also equal to small r. So, actually, CM equals to small r. Okay, so we found out that MD equals to small r and CM also equals to small r. Then we defined line segment PM as x, that is to say, PM equals to x. So CP must be equal to CM minus PM, that is to say, CP equals to small r minus x. And then we created 2 equations for the radius of the big circle. The first equation is that AP, P is the center of the circle, so AP equals to the radius of the big circle. And the second equation is that PB also equals to the radius of the big circle. Okay, we have two equations for the radius of the big circle. One is AP equals to the radius of the big circle, and the second one is PB equals to the radius of the big circle. So AP equals to the radius of the big circle, and AP equals to AC plus CP, but AC equals to 9 units and CP equals to R minus X. So in total we got that AP, that is the radius of the big circle, equals to 9 plus R minus X. So equation number 1 states that the radius of the big circle equals to 9 plus small r minus X. And we have the second equation for the radius of the big circle. The second equation states that PB equals to the radius of the big circle. PB equals to capital R. But what is the value of PB? PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MP plus DB. So we got that the radius of the big circle according to equation number 2 equals to X plus R plus 4. Okay, so we have two equations for the radius of the same circle. Of course they are equal to each other, so we created equation number 3 that states that the radius of the big circle according to equation number 1 equals to the radius of the big circle according to equation number 2, or capital R equals to capital R. From equation number 3 we got that X equals to 2.5 units. X, that is actually PM equals to X, equals to 2.5 units. So we have equation number 1 that states that capital R equals to 9 plus small r minus X. We substituted X by 2.5 units and we got that capital R equals to 6.5 plus small r, and we also know that X equals to 2.5 units. Okay, in the next step I presented rule number 5 and we implemented rule number 5 on our two circles in the drawing. Rule number 5 states that if two circles have an internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So according to rule number 5, if two circles touch each other internally, then the distance between their centers is equal to the difference between the big radius to the small radius. Okay, so we implemented rule number 5 in our two circles. We have two circles with an internal length between them at point N. They touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, this is QP, equals to capital R minus small r. Okay, this is the implementation of rule number 5 in our two circles. QP equals to capital R minus small r. So from equation number 4 we got that capital R equals to QP plus small r. But we have already found out that capital R equals to 6.5 plus small r in equation number 1. So we have two equations for the same radius, or two expressions for the same radius. So of course they are equal to each other. we created equation number 5 that states that the radius of the big circle according to equation number 1 equals to the radius of the big circle according to equation number 4. And from equation number 5 we got that PQ equals to 6.5 units, and we have already found out that X equals to 2.5 units. So then we connected together by a straight line points Q and P, and created triangle QMP that is a right triangle, because angle QMP is a right angle, therefore triangle QMP is a right triangle. And we implemented the Pythagorean theorem in the right triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus QM square. Okay, according to the Pythagorean theorem, PQ square equals to PM square plus QM square. But we know that PQ equals to 6.5 units, and PM that equals to EX equals to 2.5 units. So the only missing variable here is the radius of the small circle, QM, that is the radius of the small circle, small r. So we put the data inside this equality, and we found out that the radius of the small circle equals to 6 units. Again, the radius of this small circle, that is small r, equals to 6 units. Okay, thank you very much.